Polymers have had great success in many industries, from plastics to medicine since the 1830s, when the first synthetic polymer was created by John Hyatt. Afterwards, the first completely synthetic polymer was created in 1907 by Leo Baekeland. Polymers have had many uses over the last 2 centuries. However, possibly the most interesting and innovative branch of polymers to exist today is in nanomedicine, where blood copolymers are used to deliver drugs directly to infected sites in the body. There are 3 types of copolymers. First, we have the alternate copolymer, which is the type you have been introduced to already. Secondly, there is a random copolymer, where the monomers are ordered randomly in the chain. Lastly, we have blood copolymers, which we will focus on in more detail as it is a key to nanomedicine. A blood copolymer is comprised of 2 or 3 different monomers and measures 10 nanometers to 100 nanometers in length. The ones we use in nanomedicine are amphiphilic, meaning they have both hydrophobic and hydrophilic ends, and we prefer to make either diblock or triblock copolymers. They are biodegradable and non-toxic. Blood copolymers are synthesized via living radical polymerization. From your work in A-levels, you should know the mechanism of free radical polymerization. Living radical polymerization is similar yet differs slightly as it has no termination step. Firstly, the initiation step must be faster than the propagation step. The reaction keeps going until all monomers are part of the polymer chain, even when the ends remain active and react further. This is very useful as we have complete control over how long each segment of the chain will be. The formation of copolymers for drug delivery is called micellization, which is strengthened by van der Waals and hydrogen bonds. So why use living radical polymerization? LRP is very useful as it allows us to control how much of each monomer we have and in which order they are formed, and thus its molecular weight and chemical composition. The fact that block copolymers can self-assemble with LRP is important. The architecture of block copolymers is important as it is the shape the blocks form which allows us to place a drug in it. Success has been seen using star-shaped block copolymers for delivery of anti-cancer drugs. The star-like structure has been found by C. Yang et al. To be able to hold more of the drug as well as have greater kinetic stability than micelles made from cholesterol-initiated diblock analogs. Until recently, cholesterol-based drug delivery systems were deemed some of the best and most widely used, specifically for anti-cancer, anti-malaria, and antivirals. Even with blood copolymers, many are cholesterol-based as it is lipophilic along with various other reasons. Star-shaped block copolymers. Star polymers are branch polymers consisting of several linear chains linked to a central core. Star copolymers can be formed in one of 3 waves. Core first, whereby living radical polymerization chains are added to a multifunctional core with a known amount of active ends. All the initiation sites must be equally reactive and have the same rate of initiation. As mentioned previously, the initiation step must be faster than the propagation step, and not many multifunctional initiators do so, thus it is not the best method. Another approach is to create the arms first and react them with multifunctional electrophile, acting as a linking agent. This is the best method as you have absolute control over the process. The last method is when a living polymer precursor is used as an initiator for a difunctional monomer. Difunctional monomers are used for adding branching sites to polymers, such as a star copolymer. But how do drugs get delivered? As we mentioned earlier, block copolymers used as drug carriers are amphiphilic and often star-shaped. In amphiphilic block copolymers, the hydrophobic areas are used to carry and store the drugs, which in this case should be hydrophobic too. When the drug entrapped in the block copolymer reaches its target site, it can be released by degradation of one of the blocks or a change in temperature, or it can be designed to react to other stimuli such as pH. Benefits. Some of the key advantages of using block copolymer micelles to deliver drugs is that normally drugs may not dissolve and deliver to the target site in the right concentration due to low solubility or being lost along the way. Furthermore, specifically with anti-cancer drugs, they can damage organs or tissues along the way. By providing this polymer casing, the drug doesn't get released until it reaches the target site, hence preventing these issues or at the very least minimizing them. This means that there are less side effects than with using traditional cancer drugs.